and bottom stress. And so I like to explain it to lay people as it's basically wind pushing one way and friction pushing the other. And those are the two things that I've really focused my studies on. So storm surges pose the greatest threat to life and property during a hurricane. And just for reference, Katrina caused a maximum storm surge of 27.8 feet in the Gulf. So computational modeling is great for real-time forecasting. So this is a screen grab from some of the AdCirc people who or one of the storm surge modeling communities as Hurricane Matthew was approaching the coast. So based on what the predictions of the storm are, then we're able to figure out kind of what storm surge should be expected, since again, this is the primary threat to us. But it's also useful for long-time planning. So long-term planning and risk analysis, or understanding what's your risk of storm surge at a given location. And then this is used to inform like your flood insurance rates. Okay, so I'm going to talk kind of about both of these. So for long-term planning and risk analysis, kind of some of the work I've done is helping structural engineers develop approaches to mitigating or reducing storm surge risk. And there's kind of 4 approaches you can take. Natural approaches, so that's kind of what's already there that's mitigating storm surge, so like wetlands or natural features that increase the friction and reduce surge. And then nature-based, so things that we add in but that replicate kind of those natural features. And then there's also structural approaches that kind of hard engineers are more used to, so build a dike or build a levee. And then non-structural approaches like policy or things mandated retreat, so making people move away from areas that are prone to storm surge. But to understand your risk, you kind of have to know, to inform your mitigation strategy, you have to understand your risk. So for most risk assessments, they're based on historical data. So the problem for hurricane storm surges is that we just don't have enough data. So especially for one given location, then the likelihood that you have enough storm surge data historically to come up with the statistics that indicate your risk is small. So computational modeling is very important for this. So what you can do is, if you do have enough data, you can model the tail end of the distribution. So here I'm just showing like a histogram of storm surge heights for a number of storms, and then you don't care about the things that happen often. You care about the low frequency but high impact events. So we care about the tail. And what you can do is, if you have sufficient data, you can use it to model the tail of the distribution. So we'll define kind of what's described as rare based on a threshold parameter, and then we can fit this model. But to do it, again, you need enough data to get some idea of what the extreme values look like. And this is where this becomes difficult with historical data. So once you have modeled the tail of the distribution, you can more or less invert it. So this uses the same parameters, and then you come up with your return curves. So you'll often hear engineers talk about the 100-year flood or 100-year storm surge. And what it means is it's a measure of probability that you're exceeding that height. So if the 100-year storm surge is 3.47, so if it's here, meters, then what that means is there's a 1 in 100 chance that that height occurs each year, right? So it has nothing to do with 100 years, it's just the denominator and the probability. And so same with like a 500-year flood height, it's the probability that you, it's the height that has a 1 out of 500 chance of exceedance each year. So here, the 500-year flood is 4. Okay, so you get the return curve from the extreme value distribution, which is based on data, hopefully. But in the case of storm surges, you don't have enough data. So what we do is we create data. So we can take synthetic storms, and in particular, they can correspond to a given climate scenario. So if you have a climate model, you can downscale climate model data to develop kind of what do representative hurricanes look like for that climate. It's not my work, it's meteorologists' work. And then with that, we force our storm surge model, and then I can get the number of hurricane storm surge data that I need for the distributions. Okay, so we take kind of a sample from the storms that are generated, and we choose the ones, if we care about a particular area, we'll choose the ones that come close, which means they're within 200 kilometers, and then they're at least tropical storm strength. These are the ones we want to study. And then the climate scenarios that we used for some particular work, you could use any climate data in theory, but we use NCEP NCAR reanalysis, which is to represent the current climate, and then kind of the highest emission scenarios of various climate models to also represent what happens in the future. So what does a storm in 50 years look like based on whichever climate model? Okay, so then we can get the distribution for the storm surge height, but flood is also dependent on sea level rise. Sea level rise is a local characteristic, so you also have some distribution for there. So usually in like the news, we'll hear people about mean sea level rise or global mean sea level. And you know, for this, if you're studying a particular location, you really should look at the local sea level rise. So what's expected based on the properties there. So here we didn't model this distribution, we just used a discrete distribution. We can compute these joint probabilities to really get the return curve for the total flood. So for this particular project, we studied 4 different sites, including Jamaica Bay. That's what I'll show the results for. So Jamaica Bay is at the bottom of Long Island. And then also 3 other communities that I won't discuss here. But these communities were identified as being susceptible to flood, and then they're also socioeconomically vulnerable. So kind of from a policy standpoint, you want to know not only who has the most, who is at risk for the highest hazard, but who's the most vulnerable, and then maybe that informs how you allocate resources. So we did the methodology I just described. So if we compute the return curve based on the NCEP NCAR reanalysis data, then this is the return curve we get, where we're seeing that the 100-year flood is 3.3 meters for Jamaica Bay. And then when we add sea level rise for that same region, projected for 2040, then we get this green curve. It moves up, right? So we're actually combining our distributions. We're not just adding statically what was the mean. And then we get this green curve. So what's that saying is that if you account for sea level rise, what is the 100-year flood today becomes the 57-year flood. So if you're building some structure to withstand the 100-year flood, right, it's inadequate in 1940 because of sea level rise. If you
the increase in the return level for a particular return period, is it not equal to the mean?
It is not equal.
Okay.
So here it looks like it's just right above. Maybe it comes out that way, but it's not. Like if you look closely, you can kind of see that it has like some different bumps. So it's not just statically adding. Okay. And then if we do later sea level rise projections, then you get even more risk. So what was your 100-year flood becomes your 29-year flood, right? So, I mean, most structures aren't built to live for 100 years, but if you were, then it's not going to be adequate at the end of the century. Okay, but that's only considering sea level rise. What we know is that climate change will affect storm climatology also. So it's not just that the sea levels will rise, it's that your hurricanes will become more intense, and most people agree that they'll also become more frequent, right? So this increases risk as well. So we use the downscaled climate models to account for this. So here I'm just showing the results from one of the climate models, GFDL, which is in Princeton. But if you use a different climate model, then you'll get something similar, but slightly different. So the first thing, we can use GFDL's representation of the current climate, and then we get this dashed line, and we're seeing, well, in theory, it should be exactly the line that comes from the NCAR NCEP reanalysis, or the observed data. Okay, so it's under. So what we're seeing here is that there's some uncertainty in the climate models, which probably in here, we all know that. But because we're really just studying the change, then it's okay, right? So I'm not going to talk about, what does the sea level, or what does the 100-year flood become? I'm going to talk about what does this particular height, how does its probability change? But it is kind of an area we've discussed, kind of how do we figure out how to incorporate this difference so that we're kind of like fixing or correcting for the uncertainties we can see are there. So for this one, for MSEP, we saw that the 100-year surge became the 57-year surge. If we also account for the changing storm climatology, then the 100-year surge becomes a 34-year surge. So what we're looking at is this blue dashed line, how does it compare to the green line? So what was the 100-year flood? Where is it on the green line? So it's the 34-year flood, okay? And then if we look at the next year, so now we're accounting for the sea level rise and the changing storm climatology. So when you ignore the storm climatology, the 100-year becomes the 29-year. But if you account for the storm climatology, the 100-year becomes the 6-year by the end of the century. Okay, so kind of the point there is that, I guess the point that will kind of tie through all of the work is that there's definitely uncertainty, but our risk of storm surge is increasing, and not only because of sea level rise, also because of the changing storm climatology. Okay, so we put all this work, did all of this work for all of the site. So what you're seeing here is the year is increasing, right? So your flood risk should increase as the years change because of the sea level rise and the changing storm climatology. And then you're just seeing different exceedance probabilities. So this is the 100-year flood, this is the 500-year flood, and this is like 2,500-year flood. So we make like a matrix, so you could look at different risk levels. Ideally, you would want to look at like a return curve, so you'd have all of the probabilities. But if you want to visualize it spatially, this is one way to do it. So there's actually a book called Structures of Coastal Resilience. Now I brought it, but it has all of this work, and it's written by the civil or structural engineers that were involved in the work. So it's kind of their perspective, but then includes the results of the modeling. And then we should have a forthcoming paper just showing the storm surge results also. Okay, so that's one way that we can use computational approaches for risk assessment. So the risk assessment was based on hydrodynamic modeling, and that's kind of more my core area. So modeling is useful for risk analysis, as we said, but then it can be used for a lot of other things. So maybe trying to model saltwater intrusion or contaminant transport. Also trying to hindcast or forecast storm surges. So hindcasting is useful if you want, there's not a lot of data out there even today. So if you want to know kind of what were the storm surges at a particular location for Hurricane Sandy, you might hindcast it. So run a storm surge model for that wind field. And then forecasting obviously is great for real-time emergency management. So the hydrodynamic models that we use are based on the shallow water equations, which assume that you have a large horizontal scale relative to the vertical scale. So shallow, even though it's the ocean, because we're talking about near shore. And then if you make that assumption, you're able to depth average Navier-Stokes, and then you get the shallow water equations. So I didn't show them, but I could have. They're just a set of PDs. So the two models I showed here, on SLOSH, so that's the operational model of the National Hurricane Center. And then this is a figure from ADCIRC. So this is another model that a lot of local emergency managers are using, but it's not the official operational. Okay, so usually emergency managers will use some combination of information from both. They both kind of have pros and cons that allow you to pick and choose based on your application. But again, I want to talk about kind of the uncertainties. So if you try to model hurricane storm surge, it's going to have some uncertainty. So you can compare it to what actually happened by taking, for example, storm surge residuals. So subtract off the tide, and then what's left is the storm surge. It's what's above the tide. Then you can compare that to maybe what your model gives you at the same place. And what you'll find is that almost always they're not quite right. okay? And so this is due to a lot of reasons. So one, we're approximating the physics, right? We're depth averaging because we're assuming we have a coastal ocean or a shallow body of water, and then we're approximating a lot of other things also. So I think I will show you how we parameterize bottom friction, for example. We also numerically discretize the equation. So the shallow water equations are a set of PDEs. We're not solving those analytically. We're discretizing the region, and so that's introducing numerical error. And then you're specifying boundary and initial conditions and model parameters. So there are model parameters that we just adjust so that they match data. So there's a lot of uncertainties in the things we use to even get the results out. And then just in the process itself, there's random variation. So in storm surge, we have fluid flow, you have an idea what it's going to do, but there's some random variation there anyway. So all of this leads to model uncertainties. So kind of a lot of the work I've done connects because I'm trying to reduce these uncertainties in various ways. So one of the publications we just put out was about the parametric wind field in slosh in the operational model. So a lot of times you're not able to fully represent the wind field of a hurricane as a hurricane if you're hindcasting or forecasting, right? You don't have the wind data everywhere. You have just a few parameters like the maximum wind speed or the radius of maximum wind, the forward speed, etc. For this reason, ever since the 1960s, when people started forecasting storm surges, we parameterize the wind field. So let's just take those parameters that we do know, what's Rmax, what's Vmax, and then create the profile that shows us kind of what should the wind look like across the whole storm. But of course, this is just an approximation. So you'll model the wind profile as some function of R. So we usually assume it's radially symmetric. And then you'll also add on the background wind. So the background wind of the environment is what makes the hurricane go. Okay, so you can add that on top. And then you get some approximation of the wind, so a parametric approximation. But the ones that are used, there's, of course, many uncertainties in this. They're not going to be exactly right for every storm, for every place. Okay, so some of the work we did was replacing the parametric wind field with one that was more physically based. And so this is just one of the results. It's definitely the good results. Okay, so there were some that weren't as good. But for this simulation of Hurricane Irene, the slosh originally overestimated the storm surge as 6.8 feet. So the true surge at Norfolk is what I'm showing here, was 3.9 feet, and the slosh model overestimated it. In general, the slosh model tends to underestimate, so what we were trying to do is see if we could fix this wind field to correct for that. So we adapted the wind field and then got the model to exactly reproduce the true storm surge, okay? But that is the good result. That wasn't the case for every storm we ran. So we definitely have more work to do to see what other changes we can make. So that's obviously not the only source of error in the model or source of uncertainty. So there's many things to explore as far as how we can make the model better. Another way that I've tried to address uncertainty is just in specific parameters themselves. So wind plays a major role, but then the other major role is the friction, right? These are the two things that are fighting. So this is actually work from my PhD, where I tried to come up with a more mathematical approach to estimating bottom friction. So Mannings N is a parameter that we use to describe bottom friction. Okay, and so the bottom stress terms are the momentum equations, and so you have to define them based on your spatial domain. So you can define them in terms of this quadratic drag law. So Q also has a velocity component. Okay, so it's quadratic in U, and then it's dependent on this variable CF. And then CF is defined in terms of how much water is above the bottom surface, and then this parameter n, right? So the parameter has no physical meaning. It's used to represent friction. Okay, so it's spatially variable. So this is a graph of Manning's n for Galveston Bay. So this is Galveston Bay, and Houston's up here somewhere. And so it's used to kind of represent what's the roughness, what's the friction on the surface that you're studying, because this is what's going to impact the way the surge flows. So usually you'll obtain the values from some charts from a land cover database. So if you've taken like fluid mechanics and can think back, then we teach this like in the later chapters where you're studying like open channel flow. Depends on Manning's n also. So it's used to describe that, but it's just a table. So you're literally just looking up what should it be, what's there, and then what's the Manning's n coefficient for that. So obviously there's a lot of uncertainty there. And then it's also often used as a tuning parameter. So we know there's uncertainty in this value, so if we're trying to hindcast and match our model to actual data, then it's a like good candidate to just adjust. Maybe the Manning's n was wrong. And then this is just kind of showing sensitivity to the Manning's n. So I'm letting Manning's n range from 0.0005, so it's very small value, up to 0.2. So the smaller value is representing less friction, and then the higher value is more friction. So what you would do is say, if you know that there's trees in the region you're studying, then you would go look up in the table what's the Manning's n, and then you'd put that into the model, that's what the friction should be there. And then you can see here kind of the impact on just a tide. So the higher tides correspond to less friction. So the goal is, can you estimate this parameter? It's important, right? So you're seeing the sensitivity here. Even the magnitude of the value is small, but this is just one location showing how much the amplitude of a tide could differ if you don't get it right. So yes, I have like a mathematical background. So the question I was trying to solve was, can I find a more mathematical approach than just tuning to figure out what it is and trying to back it out from data. Okay, so I think I'll just go a little bit faster through these pieces, but if you're really interested in it, I know all about it and would be happy to talk to you later. So let me just kind of walk you through the highlights of the method. So the method that I came up with belongs to a class called statistical data assimilation. So the benefits of statistical data assimilation method. So you're going to combine your data with your model to make the model better. Okay. So what it looks like in practice is you have some model, that's the red, and then you have the truth, that's the green, right? So you know that your model is not matching what's actually true. And so you also have like data or observations at a few points in time and or space. So what you'd like to do is use that information you have from the observations to kind of project. So your model's going to project, but then when you have an observation, you're going to use that to kind of correct your model and then keep running your model forward, right? For a dynamical model. So what's beneficial about it is that you're going to, in the end, hopefully improve your model forecast. Okay, so the goal is to get this red line closer to the green line, and so the purple line is the data assimilation part. So there's still some error, right? We don't expect it to be perfect, but hopefully it's better than it would have been if we didn't include the data. So if you're from a mathematical community, then maybe you're familiar with other methods you can take for data assimilation. They're called variational methods, but they require more or less taking derivatives of large models, right? So this is difficult. So these methods kind of sit on top of your model. You don't have to do anything to your model. And then you also get a quantification of your uncertainty. So you have to make this work, kind of define how much uncertainty is in your observation and how much uncertainty do you think is in your model. And then how it works is it tries to minimize those two. So it combines it, but if you're very sure that your data's right, then it should weigh that heavier, right? If you're not so sure about your data, then it doesn't weigh it as much. Okay, so it's better than an average, and then it spits out to you, if that's true about the uncertainty of your model and data, what's the uncertainty in this new prediction? Okay, so what you do is you have some initial state. So think of the x, the state, as like the water elevation. And then this little subindex is defining the time. So your water elevation at the previous time will be projected by this model, right? Your model will take the initial condition and tell you what happens at the next place. So XF is the model state's forecast, right? It's what's the water height after I run the model. And then this PF is a measure of the uncertainty. It's the error covariance in that. So what you're going to do is come up with this analysis. So the analysis is what it gets corrected to. Then it's based on what you had at first and then a weighted difference. So the difference D is taking the difference between the observation Y and then the model or the state. Okay, so if I have my water height that came out of the model and then I have an observation, if they're not different at all, then I think it's doing a good job, and then I should not update this at all, right? So it would be, D would be 0, and then XA would just be XF. I would leave it alone. Okay, but if they're different, then I should be updating it. I should add to it. So XA is the analysis based on the data. Okay, and then what's nice is that you also get an analysis of the error variance. So after you do this, you get some measure of how much confidence do you have in that. And that's important. So people want to know what's the answer, but more and more people are asking, is that answer right? Okay, so this method gives you a way of telling them. So this is kind of the process in a picture, that you have some initial state and some model parameters like bottom friction that you'll put into the model, and then it'll give you out a forecast of that initial state. And then you'll combine the forecast with your observations, and then that'll allow you to update, and then you can just keep repeating, right? So it should do better and better as you have more data. So we have this published earlier in my career where you're updating the state. But the problem is that you're never updating what was actually wrong, right? So if the bottom friction was what was making your water heights wrong, modeled heights wrong, you never correct that, okay? So you only correcting what you're saying the water elevation is. You're never getting to the source. Okay, so the other part of my work has been, can you fix that too? Okay, so what we did was we just redefined what we called the model, and then kind of adapted everything to work for a parameter. So here I have my parameter, so bottom friction W, and then I think from one time to the next it's probably not changing, okay, so it's like a static thing. And then if I use that parameter in the model, then I'm going to get out the model output, which is a water elevation. Okay, so I will consider the water elevation I get from the model using the wrong parameter. It's an observation of that parameter. And then I can compare that to the data and then update based on the difference. Okay, so it's the same idea, it's just redefining what you call your model state. So this allows you to update the model, okay, and then you can repeat again and again. So you observe the parameter through your model and then compare that to the data. Okay, so these are some results that just show that it works. Okay, so we're using a toy mesh. Okay, so very, very small problem in our coastal modeling world. And so the goal is then to estimate the Mannings N coefficient. So what's happening here is the truth is 0.01, right? So the values are small, but I'm starting with some incorrect initial guess, and then I'm updating it with my method with data to see if I can get back the 0.01, and I do pretty good is the point here. And then here I show of the results if I have another true value, right? So 0.1 is like not very much friction. So I'm able to estimate pretty quickly that what it should have been, even if I start from like a really wrong guess. Okay, and so what we found is that the method does work, but the higher the friction coefficient, the more difficult it is to recover. Okay, and that's because I could show you, but if I go back to the plot with the tides, you'll see that the changes are, it's more sensitive for the small Mannings N, so it picks up on the differences faster. Okay, so this is a lot of my work has been data assimilation methods. How do you use it to improve your model output, and then how else can you use it to improve your model input? And what's kind of interesting about this work is that, right, I defined everything kind of abstractly. So my application here happens to be a coastal ocean model, but in theory it should work for any dynamical model, right? So whatever your M is, whether it's a AdCirc or storm surge model, or whether it's morphodynamic model or something else, then you should be able to use the same ideas. Okay, so that's most of the stuff I've done on coastal erosion or on storm surges, but now we're starting to do a lot with coastal erosion too. So this is actually the work of my grad student, Cheatham. And this is an undergraduate research student in our group, so they gave me most of the stuff for this part. But this is one of the directions we're moving. And then there's another student that's just in one of my classes, but he's done a lot of work on beach renourishment that gave me a lot of this stuff as well. So coastal erosion, this is a picture illustrating it. So what you're seeing is kind of this thin beach. It's a loss of sediment from the shoreline, and it's a natural process, okay? So this is something, it's not, you should expect it to happen, but it can be bad because it can cause property damage and exposure to hazards. So I think these images, these are Kelsey's, but I think they're from Hurricane Alberto and from Lido Beach, she said. And so it's just showing that while the more erosion you have, then the more impact a storm surge could have, for example. Okay, and then she also did some work just looking up what were the implications for Lido Beach. So it's causing property damage, right? There's a big financial cost of erosion. So if you have like beachfront properties, and you need your beach to be there, or else it's not going to be worth as much. So one of the solutions to erosion is beach renourishment. So here you're seeing before, and then here you're seeing after. And this is the picture from Chris, who's actually works for a company that does this. So sand is dredged offshore and then just pumped back onto the beaches. So the beach is eroding, find the sand and put it back, or find some sand and put it back. And so his work was in Sand Key, Florida, which apparently is not that far from here. And so he worked on a project recently where they restored 7 miles of coastline over 8 months for $52 million. So it's expensive as far as the time and the money that it takes to do this. And what's wrong, like similar to the state estimation in data assimilation, is you're fixing kind of the symptom but not the cause, right? So you can put the sand back, but it's a natural process. So eventually it's just going to have to come back. And I talked to a civil engineer the end of last year who was explaining that they basically have these projects every 10 years for the same place, okay? So, I mean, it's a great way to keep yourself in business, right? Because it's going to get eroded again. So it's a repetitive process. So if we think more about the causes, there's several, but in particular, one of them is wave energy, right? So the waves are abrading the shore. And so we started off doing a study just on wave energy. So this is an equation for wave power that is generally used. If you want to estimate how much wave power is in a location, usually just take the wave period, take the significant wave height, and then put it in this very simple equation to understand the power. So what's the kilowatts, or the energy per second per meter. But we found that this is actually a simplification of this much more complicated formula that uses spectral wave data. Okay, so the reason that the simplified one is often used is because this data is much easier to get than the full wave spectral data. So we wanted to see what's the impacts of this. So this paper is in renewable energy, where we're trying to assess what was the wave energy at various locations in Florida, and specifically we wanted to check what were the difference in those equations. So everyone's always using this equation, and is that okay? Okay, so what we found is what we could have guessed that wave power is spatially and temporally variable. But we found that the use of the simplified equation underestimates wave power by an average of 15%, which is small, but not that small, right? You can imagine over time that probably makes a big difference to whether your beach is eroded or not. There's a need for numerical wave modeling in order to assess wave power in most coastal regions. So here we're using data from the National Wave Buoy Center, or NBDC, National Buoy Data Center or something. So it's sparse. It's only in these places. And the reason we only use the red locations is because those were the places that had not just spectral, or not just the standard data, the wave height and the wave period, but also the wave spectrum, right? So we found that if you use the simplified equation, then you're underestimating, and we found that it varies spatially. So basically, for most places that you're going to just happen to care about, it's not going to be one of the places that has spectral wave data. So there's a need for numerical wave modeling so that you can get the spectral data wherever you want it, wherever you need it. We also found that the highest estimated wave power was at Cape Canaveral, and it was about 7 kilowatts, which I think if you fully harness, well, this won't make sense. I'll say in a minute the end of that sentence. Okay, so it's over here. We did find there's more wave energy on this side than this side. Okay, so originally we started studying this because we were interested in wave energy conversion. So remember I started off talking about coastal erosion, right? But that's not actually where we were going at first. She specifically wanted to study wave energy conversion. So renewable wave energy like wind or solar are popular, but her question was, what about wave energies? We're in Florida, we're surrounded by ocean. It seems like this would be another promising place. So our first step was how much wave energy is even there. Okay, and the answer is compared to Europe, not very much, which is why it's not being used. But globally, there's a lot of unutilized power in waves. Another benefit of wave energy over other technologies is that it's very predictable. So, right, we can predict the tides, we can predict the wind-driven waves, as opposed to sun. I mean, you can predict weather, but you don't know that it's going to be sunny long enough for you to have solar energy. So, right, one of the big problems in solar energy is how do you store it, because sometimes you have too much, and then sometimes you don't have any. And implementation of operation and wave energy converters is costly. Okay, so that's the main reason we don't see it. The cost of actually putting in wave energy conversion farms is expensive compared to other sources. Okay, so because there is kind of this interest in renewable wave energy, people are looking at the environmental impacts. What does it do? Okay, and so what does it do ecologically, but also what does it do to the hydrodynamics? And more recently, what does it do to the morphodynamics? Okay, so this is a picture showing the change in significant wave height with and without a wave energy converter. And so most of the studies she's found are overseas, they're not here. So this is a paper, not this one, not this. So this is a paper from 2018 that showed that wave energy conversions were reducing wave heights by up to 18%. So that is this picture. And then a later study, or another study, I think it's even the same group, but they showed, well, you're reducing the wave heights, you're reducing the wave energy, right? So our idea is, well, if you are reducing wave energy, then isn't this a good, promising approach to coastal erosion? Okay, so that's what we're working on now. We're trying to study this. So these are the preliminary results. So this is some picture I haven't looked at enough, but it's showing erosion. So this is a 1D model. It's X-Beach, but it's X-Beach gravel. So we're still there in the early stages of her work, but this is like a beach front, and then here's some waves, and then what you're seeing is kind of this eroding and then being deposited underneath. And so what I asked her to do was just reduce the wave height according to what happens in the literature, based on what the literature is saying, experimental studies and whatnot. So if it's reduced by 17% with a wave energy converter, if the wave height is reduced by 18%, what does that do to the erosion? Okay, so this is what she's showing, that smaller wave, then you have a smaller erosion. So we really want to take this much further and study for like an actual location. So if we actually implemented it for like Florida, you know, how much of that wave power that we found is available can we prevent from reaching the shore, from capturing it and converting it to wave energy. So several studies have shown that wave energy converters reduce wave heights and coastal erosion rates. And so the conversion, it's providing a green solution to both energy demand but also coastal protection needs. And there's no studies that have assessed impacts for coastal regions in the US. All of them are for Spain, the UK. There's a few in Mexico, but it's countable. So she reviewed like all of the literature she could find for where these types of studies have been done. And then also the studies have not accounted for climate change. So most of them are looking for, in today's wave climate, what does it do? So an interesting question we have is, okay, what about the future wave climate? So the next stage of her research is to address these gaps. So we want to create the morphodynamic model for Florida or for some real beach in the US, and then parameterize somehow what's the effect of the wave energy conversion, and then see what's the effect on the coastal erosion. Okay, so the key takeaways I want to give you today are: one, computational modeling provides a promising approach to a number of problems, right? So there's a lot of things we care about that we just don't have the observations for, so we model them. However, models are not without uncertainties, right? And so another vibrant research area is, how do you represent the uncertainties, and then how do you reduce them, okay? And then this is something that's becoming increasingly important as the climate changes. Okay, so that is all.
So on that wave energy